Thank you. It's a pleasure and honor to address this group, this wonderful event. And as Jim was saying, my base is Columbia University, but every so often they let me out to go out and try to spread some of the ideas of modern physics to general audiences. And for the most part, the audiences that I speak to are adult audiences. But I got an invitation a few years ago to speak to a second grade class. It was the first time I'd ever spoken to a second grade class. And perhaps I shot a little high. I wanted them to give a chance, to show me what they had learned in math and physics. So I asked them a couple questions on string theory. No, actually, I asked them a division question. I said, how do you do 3 into 6? A bunch of hands went up. I picked on one girl. She charges right to the blackboard. She takes the chalk. She draws a big old 6, and she puts a 3 into it. Not the answer that I expected. Not the answer I was looking for. But for me, that was a wonderful moment because right there you see it, right? You see who we are, right? We are a species that wants to explore, right? We start out not worrying about being right or wrong, not trying to please someone, not trying to find the expected answer, right? We are willing to charge into the unknown. That's how we begin. There's another story. It's not mine. You've probably heard it, but it's worth recounting. I heard it from my friend, the great educator, Ken Robinson. He tells a story again that happened to be a second grade class. The kids are all drawing at their desks, and the teacher goes up to one little girl and says, "What are you drawing?" And the girl says, "Well, I am drawing the face of God." Teacher says, "Well, how are you going to do that? Nobody knows what God looks like." And the little girl fires back, "In a minute they will." That's how we begin, okay? Many of us lose that passion for exploration, right? And it's our charge, it's your charge. We teachers, right? What we are here to do is to nurture that sensibility, allow it to grow, allow it to flourish, right? That's what we do. And it is a charge which I see playing a vital role in really the grandest of schemes. Here's what I mean. About a couple of billion years ago, a special class of molecules discovered an incredible trick, right? They discovered the ability to store and to transmit information and through generations of replication to refine that information, to pass on what you can think of as a kind of molecular survival manual, right? Written right into the letters of DNA, chock full of all of the lessons that we have learned, chemistry, biology, allowing those molecules to replicate further and to survive, right? Now, of course, I'm just describing evolution, right? In a somewhat different language, in the language of passing on knowledge, passing on information to the next generation. And with that instructional trick in place, life could soar. And then, sometime later, 50,000, 100,000 years ago, we're not sure exactly when, our species, we, discover another amazingly powerful trick. We discover language. And with language, we then are able to store and to transmit information from generation to generation. And along the way, we can refine that information, allowing the next generation to benefit from the wealth of accrued knowledge coming from humankind's inventiveness, ingenuity, discovery. And that, of course, leads to where all of you fit in, right? What do you do? What do we teachers do? Right? What we do, we are the ones, the select group, if you will, that is charged with the task of refining the art of inspiring and passing on information to the next generation. So, in a sense, what does that mean? What are all of you? What are all of us? What are teachers? We are the DNA of civilization. And that means that you have the power. You and your colleagues around the country have the power to protect civilization, to allow civilization to withstand the aberrations and attacks that we are all too familiar with after November 8 of 2016. You have the power to mold the next minds so that they know about truth, they know about facts, they recognize that all opinions are not created equal. There are things about the world that we know to be true. Now, I have little doubt. I mean, every time that I have a face-to-face with teachers around the country, when I go out and lecture at times, I learn so much from each and every individual teacher. Each of us has had different experiences in the classroom, and there's so much to learn. And so what I thought I would do here tonight, in the brief time that I have, is just describe a couple of the insights that I have come upon, encountered in the past. We just did a calculation. I've been teaching for 27 years. In the last 27 years, a handful of things. Yeah, you can clap that. I don't mind that one. You know? I used to have dark hair. Yeah, you know, I see it. Oh, gee, that's like a bald spot over there somewhere. And anyway, so here are 3 of the insights that I find very useful in guiding my own approach to bringing ideas out to the world, regardless of the level, whether it's general public or my students at Columbia or the odd occasion where I have the honor to address a younger group. So, first principle, I always strive to create moments that cut against intuition, those surprising moments that go against expectation. In fact, we were just talking about this over dinner. Marilyn Simons was describing, I hope you don't mind, was describing her experience with physics not being the most scintillating of subjects when you learned it in high school. She described it a little bit differently than that. But she also described how she encountered in one scenario, one example, powerful magnets that even though there's nothing between them, somehow we're coming together. She almost crushed her fingers, she described it. And it is an amazing thing. It goes against your intuition that 2 distant objects can somehow pull each other together. Surprising moments. Now, those moments can come from something like that. They can come from the insights of relativity, the insights of quantum mechanics, or they can be more straightforward, like basic physics. And I'm going to give you one little example that I know that the physics teachers here are quite familiar with. Maybe some of the math teachers haven't seen. If you have seen this, you know, don't quite give it away. But here I just have an ordinary slinky. And in a moment, after getting this guy to sort of stop bouncing around, I'm going to let it go from the top. And I want you, each and every one of you, to think about what you think is going to happen to the bottom of the slinky at the moment when I release the top. Right? Now, there are 2 natural possibilities that come to mind, right? Either it's going to go down or it's going to go up, right? And I want you to commit in your mind to an answer. And in fact, let me just quickly say, how many think, who doesn't know already the answer, how many think it's going to just go down? How many think it's going to go up? Interesting. All right, so here we go. It was sort of 50-50-ish as I could see from up here. All right, so I'm going to let this go. Watch the bottom. Did you see what happened? Maybe not. I got a little video that's going to show you what happened. So can we shift over to my input, if you will? Can we bring my stuff? That's my daughter. That's Tracy. Daughter, too, I think is a way of describing it. And she's got the experiment, the one that I just did. Now watch, this is in slow motion. watch the bottom of the slinky. So she's about to let it go. She lets it go. It hovers in midair. It doesn't move. It doesn't go up. It doesn't go down. It just hovers there. I've known about this for decades. I still marvel when I see it. Why does it happen? It happens because if you think about it, when you let go of the top, the bottom doesn't know that you've let go yet. Information has to travel along the slinky, and it takes a little bit of time for that disturbance to reach the bottom of the slinky, releasing it from the position at which it started. After you see this, you're never going to forget it. It's those kind of surprising moments that stay with us. It's those kind of surprising moments that imprint themselves in our minds and change the way that we think about things. All right. Point number 2. I strive whenever I teach, whenever I try to bring ideas to the general public, I try to create moments that are not just cognitive. Learning is powerful, at least I've found in my experience, if there can be an emotional quality to it. Now look, I am the first to admit that when I am reading Principles and Applications of Modern Physics, it's rare that I come upon a passage that makes me choke up, you know. And that kind of fits in with most people's experience, and that's why most people out there in the world do not see mathematics and physics and science. They don't see them as subjects that reach us in some visceral, emotional way. They think about them as subjects that just sort of tickle the mind or make our brains hurt. But when you think about what it's like to be a scientist or a mathematician, to come upon a deep truth of reality that nobody has seen before, that's a deeply emotional experience. Now, one great example, Albert Einstein. It was the year, yes, you can always cheer for Albert Einstein. Albert Einstein, the year was 1915. It was the third week of November, 1915, when he is racing to the finish line, trying to complete the general theory of relativity. And he decides to undertake a calculation using his new equations. And the calculation had to do with the motion of the planet Mercury, which for a long time, astronomers had known Mercury was not doing what Newton's math says that it should do. The orbit was precessing, it was moving around. So Einstein sits down with his equations and calculates away, and at the end of the calculation, he comes up with an answer for the motion of Mercury that explains that motion. Einstein himself described that moment as giving him palpitations of the heart. That is what insight, what science is all about. And if that can be communicated to kids, it changes the way they think about these ideas. Now look, most of us, none of us are an Albert Einstein, right? But when a kid, and I've seen this, when a kid can undergo the transformation from confusion to clarity, it doesn't matter how profound the move is, but if a kid can go from confusion to clarity using the power of their own mind, it's an incredible moment, an incredibly powerful, an incredibly empowering moment to learn that you are capable of doing that. And those moments, like the moments of surprise, are the ones that stick with the young mind and change the trajectory of their thinking about education. Third point, and the final one that I'll make is, I strive when I bring ideas of science out to general audiences to at least have part of the discussion really paint the picture of the drama of human exploration, the big epic stories of discovery which can really get the heart pounding. And I'm going to finish my remarks here by telling you one such story, a story that is in the news, has been in the news now for a couple of years. It just was in the news for winning the Nobel Prize this year in physics, and that is the discovery of gravitational waves. I want to quickly tell you that story because it is a wonderful example of this arc of drama, this dramatic arc of discovery that I think can really transform one's perspective about science. Okay, so what is that story? Well, it begins with something that's quite familiar. Way back in the 1600s, right, Isaac Newton was thinking about the motion of the planets and came up with this famous universal law of gravity that allowed him with a simple mathematical equation to predict the motion of the planets. And that simple mathematical equation is one that we all know. It's this beautiful thing, fits squarely on a t-shirt. We teach it to high school kids or younger around the country, around the world today. And the success of the Newtonian view of gravity made everybody think that gravity was basically a done deal. Until Einstein came along and asked a very simple question, which is, hey, look, if you got the sun over here and you got the earth over there, how does the sun keep the earth in orbit? We call it gravity, but what is the mechanism? What is the invisible force that keeps the planets in orbit? We call it gravity, but how does gravity actually work? So this is what set Einstein out on that journey that concluded in November of 1915. And the picture that he gave the world is something quite different from the one that Newton had. It goes something like this. He envisions that space and time are a kind of fabric. And this is a 3D version of that fabric, hard to picture. So let's go to a two-dimensional version that captures all the essential ideas. It's flat when nothing's there, but bring in the sun, and Einstein says the fabric warps. Even in the vicinity of the Earth, the fabric curves. Focus your attention on the moon, because this is the main point. The moon is kept in orbit because it's rolling along a valley in that curved environment, in that curved fabric that the Earth creates. And if you pull back, you find that the Earth stays in orbit for exactly the same reason, rolling along this trajectory in the curved environment that the sun creates. Now that, of course, is an artist's rendition. It's just an animation, but there's a beautiful mathematical equation. Also fits on a t-shirt, uses some of the ideas of 19th century geometry, differential geometry, due to the greats. Ricci tensor we see up there, the metric tensor, the stress energy tensor. It's a beautiful geometrical description of how gravity works, warps and curves in the fabric of space and time. Now, many people would sort of stop at that point. That's a pretty great achievement, especially after this was observationally confirmed through an eclipse in 1919. But Einstein just sort of kept on moving. And he wrote a couple of papers in 1916 and 1918 where he came to a beautiful idea. He said, look, if the fabric of space can warp and curve, then if I were to tap the fabric of space, if I were to jostle the fabric of space, then I should send sort of ripples going along the fabric of space. Sort of like, if you have a trampoline and you've got kids jumping around on the trampoline, their motion is going to send ripples out on the surface of the trampoline. His papers suggested that this would happen with the fabric of space itself. So the picture then would be something like this. If you have two neutron stars or black holes orbiting each other, they're sending out this wave, this steady march of gravitational waves. Now, how would you ever test this idea? Well, that comes out of the mathematics too, because the math shows that if you're downstream from these ripples, you're going to feel it. There's the Earth right there. And you see it's undergoing this sequence of compressions and stretches and compressions and stretches. Now, this might make you think it'd be pretty trivial to test this prediction, but that animation is not to scale. When you actually do the calculation, the amount of stretching and compressing for a typical astronomical event would be less than an atomic diameter. So now you can see how challenging it would be to ever test this possibility. Einstein himself thought it would never be tested. But that's where human ingenuity comes into the story, right? There are a couple of individuals who said, look, we believe we can test this. And they came up with the following idea that was then built. A huge device that has 2 4-kilometer-long tunnels where they send laser beams down the tunnel, bouncing off a mirror and coming back. Now, if a gravitational wave were to go by, it would change the lengths of the 2 arms of this device, and that would affect the way the light recombines. It's called an interference pattern. And in principle, the calculation showed that this kind of a device should be sensitive to stretches and compressions of the arms of the detector by less than an atomic diameter. Incredible, incredible feat. Now, the question is, what actually happened when they turned this machine on? Well, as many of you know, on September 14th, 2015, at 5 o'clock in the morning, Eastern Standard Time, here is what happened. And I'm going to show you the data right here. It's from 2 detectors, one in Louisiana, the other in Washington State. You have 2 so that if a wave goes by, it'll cause them to both twitch in the same way and thereby rule out some more local disturbance that might have been responsible. Here's what happened. You see that signal. You can hear it. That signal right there is one of the most profound signals that we have ever had the wonderful joy of receiving. Because based on the shape of the twitch in these 2 detectors, scientists were able to work out that, yes, a gravitational wave had gone by. And in fact, they were able to work out the source. And the source turned out to be 2 black holes located 1.8 billion light years from Earth, which means that these 2 black holes, like I showed you in the animation, orbited each other and slammed into each other 1.8 billion years ago, sending out an incredible wave of space and time. If you were there, you would have been destroyed. It was huge at that point, but it was so far away. And what was happening on planet Earth at that moment? Well, single-celled life forms were on Earth. That's what was happening at the same moment. So picture in your mind's eye this wave going outward, spreading out in all directions, with part of it headed toward planet Earth. It races toward the Earth at the speed of light, starting 1.8 billion years ago, when it is about 100,000 light years from Earth. It just grazes the Milky Way galaxy, and it keeps on racing toward planet Earth. When that wave is 100 light years away, an individual named Albert Einstein starts to think about gravity, writes those 2 papers that I showed you on the possibility that there might be ripples in the fabric of space, inspires others to build the equipment that I showed you, and this wave is still racing toward planet Earth. And when that wave is 2 light days away, they turn on the detectors for the first time. 2 days later, the wave rolls by and causes the 2 detectors to twitch for 200 milliseconds. The first detection of gravitational waves. If you hear that story, or you tell that story, and you or the people that you're telling it to don't feel some amount of excitement with this kind of a result, you should check their pulse. This is really what science is about. So then what does this all sort of add up to as I conclude here? Well, there are many ways of thinking about it, but there's one particular quote of Proust that I'm fond of. Proust says that the act of exploration is not in finding new landscapes, but in fashioning new eyes. That's what exploration is about, fashioning new eyes. And if you as teachers, as we as teachers, if we can help the next generation fashion new eyes, right? Eyes that might be able to look out in the universe and think about our place in the cosmos as depicted in this beautiful picture. The pale blue dot, right? Here's Saturn from Cassini. There's Saturn. Here we are. Here is planet Earth, right? As Carl Sagan told us to think about things this way. What does that mean? It means that everything we care about, everything we fight about, all the terror, all the destruction, all the devastation, what is it all about? It's all about trying to own one little pixel of sky floating in the vast cosmic darkness of the universe. If the next generation can think about reality in those terms, I just can't help but think that that perspective, those new eyes, will help to shape a much more fruitful, a much brighter future. Thank you very much for your attention. Keep up the good fight. Thank you.